All right, today we're going to talk a little bit about some Satcom 101, some Satcom fundies. The things we're going to talk about are a little bit of the history of where radio communications started. Then we'll go into a little bit of basic radio theory. From there, we'll talk about repeaters, and then from there, we'll talk about repeaters that are in the sky, also communication satellites. From there, we'll talk a little bit about basic Satcom signal flow, how teleport architecture is a little bit different. And then we'll go a little bit further into some other Satcom fundamentals. And finally, we will do a little bit of a deep dive on some down converters. So radio communications or wireless transmission of information started with the spark gap radio. The spark gap radio is really just a spark creator. That's all it does. It just creates big, huge sparks that you could pick up, a town over, a city over, whatever. They used Morse code to transmit, information. They were quickly outlawed shortly after they were made, just because they caused so much interference across the whole electromagnetic spectrum. So as better radios that we could tune to specific frequencies came on, these guys just caused tons of interference. So they didn't have a long life, but this is really the first form of wireless communications that ever existed. So what we do now is we transmit things on specific frequencies. That we use frequency diversity, or however you want to say it. If you tune into like a FM station on your radio for like 94.7 megahertz, that you're tuning into that specific frequency, and that's where that station is transmitting at, and it doesn't interfere with the station that's transmitting at 103.1 megahertz. But a sine wave, just to get into it, is kind of where it all starts. And a sine wave is just a single pure frequency free of distortions and other frequencies. And that sine wave, the rate at which it oscillates is measured in hertz, and megahertz is just a whole lot of hertz, and so it's a lot of oscillations going on over a period of a second. So sine waves, once again, they're the building blocks of radio signals, AM, FM, tons of other modulation schemes out there. This just kind of gives you a little diagram of those different ones. The frequency is the speed at which the wave oscillates. So obviously the red frequency that you see up there, or the red sine wave, is oscillating at a lower frequency than the purple one. So just to kind of drive this home a little bit, we're going to go into some audio here. We're going to listen to also audio frequencies oscillate at different frequencies too. So the lower the frequency, the deeper the tone, the higher the frequency, the higher the pitch, right? So we'll just play this quick YouTube video just to kind of show the difference. And as you can see, they're starting off around 200 hertz and continuing up. As it goes up, the pitch increases. All right, and we could keep going, but my dog's probably going to start howling if I don't move on here. Oh, well, I guess we got to stop that first. All right, so when it comes to frequencies, frequencies are kind of like broken out into different bands. So you can see there anything from like 10 hertz up to, it looks like 10 kilohertz is kind of, or maybe a little bit more than 10 kilohertz is considered very low frequency. I think they use very low frequency to like communicate with submarines under the water. You've got medium frequency, not really sure what that guy's used for. High frequency is HF transmissions were used like back in World War II. That's how they would get long-haul communications before the age of satellites without running wires all over the place. They would bounce radio waves either between the ground and the different layers of the atmosphere, or they would reflect them off the different layers of the atmosphere back down. VHF and UHF is kind of like line of sight communications. We still use those today. All your like EMS uses UHF and VHF. Your TV, if you still use the antennas, they operate in VHF and UHF. SHF is primarily what we're going to talk about. That's where all of our Satcom pretty much lies. There is some in UHF, and we'll probably talk about that in later videos, but we're mostly going to stick with SHF. There are some Satcom capabilities in the EHF range, but they don't apply to what we do, so we're going to skip over that. It's also kind of cool just to note there too, as the frequencies get higher, you start to go up into the optical spectrum and the different wavelengths of light. This is just kind of a diagram. Yeah, I guess I just talked about most of this stuff, but yeah, satellite communications, mostly SHF. I guess radio astronomy and some other things are used in EHF also. But yeah, we'll keep going here. All right, so as you can see, we have several different bands here. We'll start off with L and we'll go over. L band is actually what your system works on. Everything inside of it's at L band. We down convert it at the LMB into L band, or the low noise block down converter on the antenna. And from that point forward, it's all in L band. S band is, I believe, used for command and control of satellites. I'm not 100% certain on that, but I'm fairly certain that's true. C band is used for communications. It was used for Satcom communications a long time ago. It's still used today, but not nearly as much as it was before. It's still used in northern latitudes quite a bit too. X band is not completely owned by the military, but mostly, almost anything that's in X band is going to be military Satcom. KU is lots of commercial and military Satcom. K is not really used for ground to satellite communications. It's used for satellite to satellite communications. One of the problems with K band is that it is very susceptible to moisture attenuation. So any kind of clouds or moisture in the atmosphere significantly degrades that signal. So it transmitting from satellite to satellite where there's no atmosphere is fine, but it transmitting from the ground up is not a good way to go. It doesn't work very well. KA is used for military Satcom and commercial Satcom. Matter of fact, DirecTV uses KA band. Anyway, the amount of throughput is going to be lower generally, and then as you go up, it's going to get higher. So KA, you have a lot more throughput on KA than you do on C, for example. The antenna size as you go down in the lower frequencies is going to be larger. So your S band and C band antennas are going to be quite a bit larger than your KA band antennas. If you've ever seen those old Satcom dishes out, usually in rural areas, the really big ones, those are your C band antennas. The DirecTV or Dish Network antennas that you see on people's houses now are KA, so you can see there's quite a bit of a size difference between the two. Then the susceptibility to rain fading. As you go lower, it's less, and as you go higher, it's more, generally speaking. K-band is completely almost, lots of rain fade with K-band. That's why we don't use it specifically for Satcom from the ground. But if you've ever had DirecTV or Dish Network during a heavy rainstorm, you'll find out what rain fading is all about because it's in Ka band. The amplitude is the power of the sine wave. So as you can see, the sine wave on top is at a much higher amplitude than the one below. It looks like it's almost double just based on my eyes here. But yeah, the higher the amplitude, the greater the power. So just a little basis to start with there. Modulation is required to place information on the carrier or the sine wave signal. One of the simplest modulations is amplitude modulation. If you can see there, that little diagram on the very left, it shows AM as it's changing. You can see it's adjusting the amplitude of the wave to transmit the information. That could be ones and zeros. It could be the voice of a person. It could be tons of other stuff. But you can see here, frequency modulation is another form of modulation, and this is another diagram that kind of displays how AM adjusts the amplitude in order to transmit information. But FM, you actually adjust the frequency back and forth. So technically, your whenever your radio station, your FM radio station is on 94.7, it's actually kind of shifting back and forth, probably up to 94.75, whatever, and then down to 94.65 or whatever. So that frequency is changing slightly within its little band. They call it a guard band, but it can change back and forth between there, and that's how transmits information. A different type of modulation, and the one that's primarily used in Satcom, though there still is some frequency modulation and so forth, is phase modulation. And with phase modulation, what they're doing is they are adjusting the phase of the sine wave. So you can see here, you got your carrier, you got your signal. A is your carrier, B is your signal. ASK is amplitude shift keying, and they're using amplitude to transmit ones and zeros, right? FSK is frequency shift keying, and as you can see there, they're using changes in frequency to transmit the information. And then phase shift keying, or PSK, as you can see on the last one, they're changing the phase of that signal in order to transmit those ones and zeros. And I have a better diagram of it coming up right here. So you can see here the signal's in phase for the zeros, and then whenever a 1 hits, it changes phase by, it looks like 45 degrees there. Possible. Nope, that's shifted 90 degrees. But either way, you can see that the different phase shifts are just transmitting ones and zeros. That's as deep as we need to go for what we do. Just to talk about a few of the different ones, there's you can shift in phase, out of phase, 90 degrees, and that would be BPSK. You can shift even more than that. With BPSK, you can only transmit a 1 or a 0, right? With QPSK, you can have different phase shifts where you're shifting at 45 degrees, right? So a different phase shift for each one. And with QPSK, you can, the same amount of bandwidth on the satellite, you can get, I think the way my tech school instructor worded it was 10 gallons of stuff in a 5-gallon bucket. So what we're doing here is we have 4 different possibilities, right, that we can transmit information with just one actual shift. 8 PSK, just different phase shifts, more phase shifts, so that we can transmit more information with less bandwidth. On a side note, though, as you get higher in those modulation schemes, the signals become a little bit less resilient, right? So they become easier to interfere with. They become more susceptible to interference, intentional or unintentional. So BPSK might take more bandwidth, but it is much less susceptible to any kind of interference that might come. So here's a quick video that shows that someone made that in real time kind of demonstrates the different types of PSK or phase shift keying going on. They did put some kind of cool tunes along with it. Headbanging is encouraged but not required. So as you can see there, just some different types of modulations. So bandwidth, we measure bandwidth at the 3 dB down point. So the way that we look at signals on a spectrum analyzer, we probably cover that more in depth in a spectrum analyzer training, but the way we look at the signals isn't linear, it's logarithmic. So if you see the 0 dB part and the negative 3 dB down part, that is actually from that negative 3 dB down part to the top of the other one is double the signal strength, right? And that's where we measure that roll off at. So if we're trying to measure the bandwidth of a signal, we go from that neg 3 dB down point on both sides and take a measurement in between the two, and that's how we calculate what the bandwidth of a signal is. Signal to noise ratio, the noise that you see on your spectrum analyzer is from background radiation, it's from heat, it's from other electromagnetic interference that's all over the place. Your signal pops up over top of that. For our purposes, we will most of the time, when we're looking at stuff, because we can only see stuff above the noise floor, we're going to want our signals above the noise floor, and we're going to want it as much above the noise floor as we possibly can get it. But the top of your signal down to the top of the noise floor is called your signal to noise ratio. And the greater that is, the greater the amplitude of the signal. All right, so repeaters. Why are we going to talk about repeaters? We're going to talk about repeaters because satellite communications, really they are just fancy repeaters in the sky. But first of all, let's talk about how repeaters work on the ground. So we've got EMS and fire trucks and police officers and everybody else in a small geographical area. They're trying to transmit and talk to each other, but if there's buildings in the way, if there's hills, if any of those things are happening, or if they are on like a walkie-talkie that only transmits 5 watts as opposed to their car that might have a greater transmitting capability, how do they get that signal out to the entire town? And the way they do that is they transmit that 5 watts up to a repeater that's sitting up high on a mountain or on a building somewhere. And that repeater translates that to a different frequency, which everybody else's stuff is set to receive. And that's how they get it, is it goes up to the highest point, it amplifies the signal, and it sends it out everywhere. These typical repeaters, depending on how high they are, I mean, they can, even sitting at ground level, they can go up out to 50 miles. If they're higher, they can theoretically go out higher than that. The radio horizon is about 50 miles, but still a lot more than, just a few miles you might be able to get with the little walkie-talkie that they may carry on their person. So this isn't a very good picture. It's the best I could find of a signal plot of a repeater in a town, and as you can see, it's covering multiple counties all around that area. So that one person, instead of just being able to transmit for a few miles and hoping there's not a hill between them and the person they need to talk to, they can hit that repeater and have it transmitted out all across there. But what if you want to transmit, real quick, we have a big repeater bank that you can see here from Building 2027 in Colorado Springs. That is the Cheyenne Mountain Antenna Farm. A lot of people think that all those antennas are DoD. Maybe some of them are. Lots of them are private and public and amateur radio and repeaters for EMS, just local radio stations, television stations, stuff like that. But yeah, tons of repeaters up there on the mountain. Satellite communications are really just repeaters in the sky, right? So you've got your transmitter, it transmits up. The satellite down converts that signal and transmits it back down to the receiver. The opposite actually happens the other way. That's not displayed in this graphic, but that's really what happens. Satellite's nothing more than just a repeater in the sky that you can, if it's UHF communications, you can reach out across a third of the globe. If it's like this right here is a KU satellite downlink footprint, that you can see that someone in Orlando, Florida could shoot a whole TV station, a conversation, internet to somebody in Canada, right there in southern Canada, or Spokane, Washington, right? So it's just a way to get your signal repeated over a much larger area. It's a lot more throughput too. So a teleport link is a little bit different. You could take for instance, you could have command and control or Facebook or whatever going on, or sending a YouTube video, I don't know, whatever you're doing. In Salt Lake City, Utah, you could send it across a fiber line, across the Atlantic to Naples, Italy, and then that teleport in Naples, Italy could send it up to a satellite link that could send it down to some place in CENTCOM where they can't get a fiber line right now. It could also be used to send it to places where you can never get a fiber line, such as a ship or a remotely piloted aircraft. So these are just kind of some of the architecture of links that you might come across. So when you, the end user, are sitting on your computer out in the desert and you are on cruising Facebook what's going on. How are you getting that link back to somewhere in civilization where they have they are connected directly to the internet? The way that works, we're going to start up here at the top. At the top on the top left-hand side here, where we have the end user, computer, phone, etc., and the ones and zeros. Right, so your computer is going to send that information out as ones and zeros. That information is going to go to a modem. That modem is going to modulate that signal and those ones and zeros into a signal that can be transmitted through the air, through the radio, right? So that was what we were talking about before with like the phase shift keying and all that good stuff. That signal from the modem is going to go to an up converter. That up converter is going to take it from what we work in with the modems, usually around called L-band, and it's going to up convert it to the uplink frequency that the satellite's looking to receive. And in this case, I just randomly chose 14.1 gigahertz or 14,100 megahertz. That is going to go then to an HPA, which is a high-powered amplifier, which is going to increase the amplitude enough to get it up to the satellite, which is quite a ways away. That satellite's going to receive that signal at 14.1 gigahertz, and it is going to down convert it by 2300 because that's usually the translation frequency for KU, which is going to bring it down to 11.8 gigahertz, and that is going to go back down to that satellite dish that is located, or satellite antenna that is located somewhere in civilization that has a connection to an actual internet trunk. It's going to go into that LNA, which is a low noise amplifier. It is going to amplify that signal before it goes into the equipment rack. The equipment rack, there's tons of electronics, and all of those electronics are creating noise, and we want to amplify the signal before the noise. We don't want to amplify noise, we want to amplify our signal. So we amplify it outside, away from everything else first. Then we send it in. It'll go through a signal conditioning unit. That'll further, there's a lot more filters and stuff in there that are going to filter out some other stuff and set the appropriate power levels so that the down converter can read it without overdriving it. When it goes to the down converter is going to take it from that 11.8 gigahertz or 11,800 megahertz into L-band, which is going to be roughly, I believe, 1050 megahertz, if my public math is serving me well there. And that is going to go into a modem, which will demodulate the signal back into digital data, which you can receive on your computer or whatever device you have hooked up to the internet. So just a little bit about what is going on in the actual satellite. I wanted to kind of do a breakout. All that's going on in a satellite is you have your signal going into, we're going to start over on the left side with the uplink. You get your signal going into the LNA. From the LNA, it's being down converted. Then from the down converter, it's going to HPA, which is transmitting it back out, amplifying it, and transmitting it back down to the ground. Same thing's going back the other direction. It's really that simple. And then I know we kept talking about down converters, up converters, all that good stuff. Down converters and up converters are pretty much the same. They just work the opposite, right? So we're just going to break out a down converter real quick so you can get an idea and an understanding of what I mean with all these words that I keep saying. So when with your particular system, you have a low noise block down converter, right? And it down converts actually at the antenna. So as soon as it receives the signal, let's say it's receiving a signal at the 11,800 megahertz or 11.8 gigahertz, right? It has a local oscillator in it, which is really just a little crystal that is creating a frequency at 10,750 megahertz, right? It's vibrating at 10,750 megahertz or 10.75 gigahertz. That frequency and your 11.8 gigahertz go into a mixer, and that mixer, what happens when you send both of those frequencies through a mixer is you get the addition of the two, the subtraction of the two, and your two original frequencies on the other side. Now, I know some engineers are going to say, well, that keeps going on and on and on. And you get all these, second order, third order, whatever. We're not talking about that. We're just going to talk about these primaries. We're going to assume there's only 4 here, and we're going to forget about the rest to make it simple. All right. So you're going to get, if you add 11,800 and 10,750, you're going to get 22,550. You're going to get your 2 original frequencies, which was your 11,800 and your 10,750. Then you're going to get the subtraction of the 2, which is going to be your L-band frequency that you actually want in your signal, which is the 1,050 megahertz that we have there. All of those are going to go through what's called a bandpass filter. You don't really need to know much about it other than the bandpass filter just only allows the bands through, or the frequencies through, that it wants to go through, and blocks everything else. So this one, I just randomly said it has a range of 950 megahertz to 1400 megahertz, which means only one of those 4 signals come out of the other side and actually enter into your system, which is that 1050 megahertz that we're actually looking for. And that concludes this particular lesson, but there will be more, and we will go more into depth on all of these things later on.